Okay, for our sample problem, the wet weight of a specimen of soil is 340 grams and the dried weight is 230 grams. The volume of the soil before drying is 210 cc or cubic centimeter. If the specific gravity of the soil particles is 275, determine the void ratio, porosity, degree of saturation, and dry density. So we have here so the figure shown is the schematic diagram for our problem. So we have here our schematic diagram. So this is the schematic diagram for our soil mass based on our problem. The total weight is 340. Our total volume is 210. And we have air, water, and solid. So we have to take note that based on our uh, discussion a while ago that the weight of the weight of the air is negligible, or that is equivalent to 0. So for this problem, the weight of the solid is 230. So we don't have the value for the weight of the water. So here we're going to solve first to start with, we're going to compute for the weight of the water. So since you are given with the total weight, and of course total weight is equal to the weight of the water plus the weight of the solid. Since we have the total weight and the weight of the solid, so which means that we can compute for the weight of the water, and the weight of the water is equivalent to 110 grams. So therefore, if we're going to compute now for the volume of the water, so that is V sub W. So that will be equivalent to the weight of the water, which is 110, all over to the density of the water, which is 1 gram per cubic centimeter. So therefore, the result here for the volume of the water, this is equivalent to 110. This is grams all over 1 gram per cubic centimeter. So we get a result of 110 cubic centimeter. Now for the volume of the solid is equivalent to the weight of the solid all over the unit weight of the solid. So the unit weight of the solid is equivalent to the specific gravity of the soil times the density of water. From the problem, our specific gravity is 2.75 times the density of the water, which has 1. So we got a result of 2.75 for the unit weight of the solid. So therefore, the volume of solid will be equivalent to 230 all over 2.75. And the volume of the solid is equivalent to 83.64 cubic centimeter. Now for the volume of the air, of course we know the total volume is volume of the air plus volume of the water plus volume of the solid. So therefore, to get the volume of the air, that will be equivalent to the total volume minus volume of the water minus the volume of the solid. And we get a result of 1,636 cubic centimeter. For the void ratio, of course, we can make use of the uh, value for, since we are given with the we are given with the volume and the weight of the soil sample. So we can have our E, which is equivalent to this equation, volume of the water plus volume of the air all over volume of the solid. And if we try to substitute the values here, we get a result of 1.51 for our void ratio. And for the porosity, of course, for our porosity, we have our equation, which is N to denote porosity. That is equal to the volume of the voids all over total volume. So we have here, you try to substitute the value, the result here. So we get a value of 110 plus 16.36. Actually, this is actually the volume of the water plus the volume of the air all over the total volume. So we get porosity is equal to 0.60. For the degree of saturation, which is equivalent to the volume of the water over the volume of the voids, So we get here a value of 0.87 or 87%. And for the dry density, we have here dry density is equal to the weight of the solid over total volume. So we get a value of 1.095 grams per cubic centimeter. Now we move on to Otterberg limits. So what is the importance of Otterberg limits? Actually, Otterberg limits is used to determine the consistency of the soil. So this was actually the name Otterberg is basically came from, it was named after a scientist wherein he was the one who studied the concept for this consistency of soil. So we have actually for a clay soil, this is actually for a clay type soil. We have to take note that for a clay soil with very low moisture content will be in the form of solid. So as we increase the water on our clay type soil, the solid will gradually become plastic and the soil can be molded into different shapes without breaking up. So as we try to continue increase the amount of water, the clay soil will behave or it will flow as a viscous liquid. So the stiffness or consistency of the soil at any time therefore depends on the state at which the soil is, which in turn depends on the amount of water present in the soil. So we have to take note that Otterberg limits is trying to describe the water content level at which the soil changes from one state to the other state. So we have here three state. We have our shrinkage limit, we have the plastic limit, and the liquid limit. So if we try to illustrate this one, so this is the illustration for our consistency limit. So we have here the water content, then we have the state, and we have the liquidity index. So for the water content, it started from 0. As we try to increase our water content, if you're going to observe, it will be in the form of liquid. So the soil will behave as liquid. So it will start for the water content. So it will start on the brittle solid. Then it will move as we increase the water content. It will behave as semi-solid. Then if you add another water, it will behave as plastic solid. And if we try to increase another amount of water, it will behave as liquid. So from 0 to this point, so that transition actually is the shrinkage limit. From shrinkage limit towards this point, so that is now the transition for plastic limit. So as we try to increase an amount of water, so from plastic limit towards this point, it have what we call our liquid limit. So you have to take note that the liquidity index also changes. So from this portion, so that is the liquidity index is less than 0. On this portion, this is equal to 0. On this part, this is the liquidity index is greater than 0 but less than 1. On this part, liquidity index equal to 1, and on this side, on this portion, liquidity index is greater than 1. So that is how we try to describe the Otterberg limits or the consistency limit. So we have to take note that our shrinkage limit, the saturated soil is slowly dried. The volume shrinks, but the soil continues to contain moisture. So the moisture content at which this occurs is shrinkage limit. So you have to take note for the shrinkage limit, we're going to have here, there is now the drying up of the soil. So there is a continuous drying of the soil wherein it will lead the moisture content at which further drying will result in additional shrinkage. So which means for shrinkage limit, so there is the soil continues to dry up, and at a certain portion wherein the soil will not dry up, meaning to say it has reached its maximum or optimum drying state, so it will not dry up anymore, and that is now what we call shrinkage limit. So plastic limit is defined as the moisture content at which the soil crumbles when it rolled down to a diameter of 1/8 of an inch. The moisture content is higher than the plastic limit. So if the soil can be rolled down to a diameter less than 1/8 of an inch, so the moisture content is lower than the plastic limit. Then liquid limit is defined as the moisture content at which the soil will close to a groove 1/2 an inch, and standard liquid limit equipment has been dropped 25 times. So you have to take what is the importance of this. Of course, it is very important. These properties are very important in the construction of highway. So these are the apparatus that is being used for to obtain the liquid limit. So this is what we call the Casagrande liquid limit apparatus. So basically, they're going to perform this in the soil mechanics laboratory, and so that you could obtain the liquid limit value for that particular soil sample. So we have what we call plasticity index. So that is the range of moisture content over which the soil in the plastic state is the difference between our liquid limit and plastic limit. So that is the difference between liquid limit and the plastic limit. Then liquidity index. Liquidity index is actually equivalent to the natural moisture content of the soil minus the plastic limit over the plasticity index. It is actually for both the PL and the LL, which can be determined only on remolded soil. It is quite possible that the limit determined may not apply to the undisturbed soil, since the structure of the soil particles in the undisturbed state may be different from that of the disturbed state. Then, of course, another important factor or engineering property is permeability. So when we talk about permeability, it is actually the property of the soil that describes how water flows through the soil. So which means that permeability is trying to get how permeable, trying to get the characteristic of the soil in terms of its permeability. We're trying to identify whether the soil is permeable or impermeable, or how it is permeable, or how permeable a soil is, which means how it will depends on how the water will penetrate within the soil layer. So it is actually denoted, it is actually being given by our coefficient or permeability coefficient, denoted by capital letter K, which is the constant of proportionality of the relationship between the flow velocity and the hydraulic gradient between 2 points in the soil. So we have here our velocity of the water in the soil, which is denoted by small letter u, equal to permeability coefficient times our hydraulic gradient. And of course, we have what we call shear strength. So this is very important. This is one of the basic engineering property of the soil, which is also important to highway engineer, because for our soil mass, we're going to the soil mass of our highways, they are actually prone to failure in shear. So the shear strength of soil depends on the cohesion and the angle of internal friction, which is expressed in this form. So shear strength is equal to cohesion plus the normal stress on the shear plane multiplied to tangent phi.